let's look into more details when we compute this partition function of a finite size system. So H is a Hamiltonian defined in the finite region omega, and we could define this Hamiltonian as a kind of a combination of a coupling constant multiplied by the interactions. Okay, the coupling constant Kn refers to the coupling strength of this interaction theta n, and n refers to the some kind of a degrees of freedom of your system. So you can sum over all degrees of freedom with the interactions, all possible interactions of different degrees of freedom. For example, when n equals to 1, theta 1 refers to sum over the spin of your system, for example, the Ising spin. And K1 is defined as your H divided by this KBT, where H is magnetic field, which is a Zeeman term. H dot S is kind of a Zeeman energy. So when there is a spin or a magnetic moment in the presence of the field, and there's a Zeeman energy, which is S dot H. And that's just the simplest possible interactions between the single magnetic moment and external magnetic field in a Zeeman form. And theta 2 describes the spin-spin exchange coupling between the neighboring spins. So I and J refers to this nearest neighbor sites, and the coupling constant K2 is given by either plus or minus a coupling constant J divided by KBT. And the sign plus refers to the ferromagnetic coupling, and minus refers to the antiferro. So ferromagnetic coupling refers to the spin orientation that is preferred for all the spins to be parallel to each other. For the antiferromagnetic coupling, the system prefers that orientation, that the spins alternating arranged on the lattice up and down, up and down. Depending on the sign of this in front of the J, you could have either all parallel or alternating spin orientations of the system. And it's called Ising or Heisenberg ferro, or antiferromagnetic Ising or Heisenberg term. So for the isotropic coupling between this SI vector and the SJ vector, we call this Heisenberg model. And you can imagine that I can have higher degrees of interaction, say theta n, say SI x quadratic term plus SI y quadratic term plus SI z quadratic term. For the system has this cubic anisotropy, where you could show some preferred axis that the spin were coupled, and either as easy axis or easy plane that spins were coupled more preferentially. And you could have such a theta higher order, say the quartic term, and so on. And you can define this K4. All right, but we won't discuss higher order term. We will keep just the leading lowest order, say theta 1 and theta 2, in our discussion. So then the partition function Z for such a Kn coupling constant is given by the trace of e to the minus beta h, where this trace defined as sum over all this, say, spin configurations, and you multiply them together. You sum over all the spins, say, of the all lattice, and so on. And then you could define the free energy as function of a coupling constant, which is the reduced coupling constant. And this K now is actually a coupling constant divided by KBT. So this is given by minus KBT log of Z. Okay, so this is the key quantity throughout our course that we need to calculate and understand the behavior of the free energy as function of the coupling constant. And to that, we need to calculate the partition functions at a finite temperature and finite size. We will approach the system to the thermodynamic limit. The important statement is this: all the thermodynamics contained in the derivative of this free energy with respect to this Kn. So remember that we define this first or second order continuous phase transitions in terms of the derivative of the free energy with respect to the coupling constant, right? And we should monitor how this first order derivative of free energy with respect to the coupling constant behaves, or second order derivative of the free energy with respect to the coupling constant across the phase transition, and see if there's a jump or divergence or whatever. And secondly, all the thermodynamic observables that you can determine experimentally are functions of free energy as derivative with respect to this coupling constant, say a specific heat and magnetizations and so on. So everything that we can measure in the lab can be determined as a function of this free energy derivative. And the question that we want to ask is that can we have non-analytic behavior of the free energy derivative? So the question we want to ask is, we know that near the phase transition, the free energy is non-analytic, but at the finite size, F is always analytic, because you could simply just numerically determine a calculus partition function at any finite given size, and simply just by taking the trace of this finite size system doesn't give you any divergence or analytic or singular behaviors, because everything is analytic. It's simply the sum of all analytic function, and you always get an analytic function at a finite size. So which means that at any given finite size, there's no phase transitions. That's really important. So the phase transition is not possible to be observed at a finite size. So this is really, really important statement. Everyone should remember that statement, that the phase transition that we talk about up to now cannot occur for a finite size system. So of course we want to ask, what do you mean by finite size or infinitely large size? And we will define that in just a moment, okay, in terms of the thermodynamic limit when this system size becomes infinity. And therefore the other sentence closely related to that sentence is that the phase transition occurs only when the system size becomes infinity. So this is another important statement, that phase transitions occurs only in the thermodynamic limit where the volume of a system goes to infinity. Okay, so this is one of the most important statements and conclusions of a phase transition in statistical mechanics, is that we like to see how this free energy becomes non-analytic or becomes singular at the transition. But this is not possible to be observed at any given finite size because of this reason. Therefore, the only limit that the phase transition can occur is that when the system size becomes infinity. Okay, so let's just put things in this order. So as I mentioned, the free energy is a function of a coupling constant, and which is always analytic. And this kind of free energy at the finite size is actually proportional to the volume of the system size. This is the omega is the domain of the space that defines your Hamiltonian, and this free energy at any given finite size of a domain is proportional to the volume of your system size, right? And when the system size is finite, so the volume is finite, this free energy is always finite. And because this partition function at a given size is actually proportional to this minus beta, this volume, and also the trace of e to the minus beta h. So we could sort of expand this free energy as function of volume times this free energy density in a bulk plus the surface contributions, which is a product of the surface area multiplied by this free energy density per unit area, and plus the other things, which we don't care. So in other words, at any given finite size, we can imagine that this free energy is simply just a sum over all these contributions inside this cubes, right? This three-dimensional cube. And this quantity is proportional to the volume of the system. And also, at these edges of this cube, we can also have some contributions to the free energy. So we could define these two quantities called the bulk free energy density, little fb, and the surface free energy density, fs, little fs. So later we will define that in a more proper way. So the reason why we should define this little fb and little fs is that we should define what I mean by thermodynamic limit. So in other words, when the volume of the system goes to infinity, we should have well-defined the bulk free energy density and well-defined the surface free energy density. So in that case, then we could say that the phase transitions could be observed in such a limit. Just as I mentioned, we can define the free energy at the finite size in terms of the bulk free energy density, little fb, and surface free energy density, little fs, and plus some contributions at the corner. So this is, and maybe there's a corner. Okay, so we simply just approximate this free energy at finite size in terms of the bulk free energy density and surface free energy density. But this kind of a approximation is accurate only if the system size L is much larger than the correlation length C. So we haven't defined the correlation length yet, but we will in just a moment. This is just a remark, and we will come back to this comment later. All right, so under such approximation, we could define the bulk and surface free energy density. So the statement is that at any given finite size, everything in this FB and FS are analytic. So there is no chance that the free energy could be non-analytic. But the only chance that this could happen is that when this volume goes infinity and the free energy density, the bulk free energy density, the surface free energy density could be non-analytic. So let's define the thermodynamic limit. So naively, this simply just tells us that this volume of the system goes to infinity, but this is just a zeroth order definition of the thermodynamic limit. The more accurate definition of thermodynamic limit is that the bulk free energy density and the surface free energy density are well defined and are independent of the volume or system size. The little fb is function of a coupling constant Kn in this limit is defined as the capital F omega, which is the total free energy of the system, divided by your system volume. And this limit exists. So this is a highly non-trivial statement, because when the volume goes to infinity, something crazy may happen. This total free energy divided by volume could be divergent. And we will give you an example of such a system where this bulk free energy density diverges. But in that case, we said that this thermodynamic limit doesn't exist, because that limit, this little fb, should exist. And this should also independent of omega, your region or spatial region of a system. And same for the surface free energy density. And we could also follow the same way to define this little fb, and we can define little fs in the thermodynamic limit. And we should simply subtract this total free energy from the bulk part of the free energy, and that is the surface free energy. The total surface free energy divided by the surface area is the surface free energy density. And that limit should also exist and should also be independent of your volume or system size. And the third quantity can be defined in the thermodynamic limit is the bulk free energy density on the lattice. Suppose that we are dealing with this lattice with n sites, and on the lattice we can define this bulk free energy density as the number of sites goes to infinity, and you take the ratio of the capital F omega to the number of your sites. And that limit should also exist, and also should independent of your system size or space. So we should satisfy these three conditions that allow us to define the bulk and surface and also the lattice free energy density. And when we take this volume to infinity and this limit exists and all independent of your system size, if that is the case, then we are reaching the thermodynamic limit. In other words, the thermodynamic limit is that when we take the volume goes to infinity, we should satisfy these three conditions. and satisfied. 1, 2, and 3. Okay, so that's the complete statement of the thermodynamic limit. In other words, this is a highly non-trivial statement that we have a thermodynamic limit because you don't really know whether this ratio of capital F to this volume or to the surface area, that limit exists. You don't know because when volume goes to infinity, something divergent may happen. And if you divided your volume of the surface area, you don't know whether when you take the volume to infinity, this ratio still be a constant or independent of volume or length scale. It can be divergent. So in other words, the thermodynamic limit is highly non-trivial. So in fluid, the thermodynamic limit often comes with the constraint because in fluids, you could imagine that both the particle number and your volume goes to infinity in that limit, but you have a finite fixed, say, density of your fluid, which is the number of particles divided by volume, which is a fixed constant. And the thermodynamic limit is highly non-trivial. And the final statement is that the phase transitions are defined only in the thermodynamic limit. So to illustrate this, our textbook tells us an example of a power law interactions, say in the fluid or in other spin system or some density interacting system. And we don't have time to discuss this today, but we will discuss this next time. But let me just briefly outline this example. This example shows that thermodynamic limits can be absent. It is not always the case that this limit exists. So in this particular example shows that the power law interacting system. So depending on what the power law of the interaction look like, and in some cases the thermodynamic limit exists, but in other cases it doesn't exist. So the interaction of the particles in that example shows a power law as a distance to these different particles. For example, in this particular case, that these interactions of a different densities, say rho 1 and rho 2 of particles, shows the interactions of 1 over r to the power of sigma, that kind of a power law interaction. So in this system, and we will see next time, that depending on this dimensionality relative to sigma, and it can have a thermodynamic limit only when sigma is greater than d. So when this sigma, the power of this interaction strength in terms of this distance greater than the dimensionality d, then we have a thermodynamic limit. In the reverse limit, when sigma is smaller than d, then we don't have a thermodynamic limit. So it really depends on the dimensionality and the form of interactions. And in the general statement, to have the thermodynamic limit is that we have more short range interaction. So if these interactions are short range, meaning when the sigma or the exponent of this power law in R is actually much larger than the dimensionality, meaning this interaction is actually cut off when distance is long enough, so that you can only consider the short range interactions between these particles. Suppose this is a really short range, then there's a long tail, but you could simply just cut the interaction at a shorter range, meaning the particle-particle interactions occur only when they close enough, and we don't care about these particles far away from each other, so they are free. Okay, they don't feel interactions, but the particles feel the interaction only in the neighborhood of that particle. So if this is the case, most likely have a thermodynamic limit. On the other hand, for the long-range interactions, as we'll see later next time, this limit doesn't exist. Okay, so this is really non-trivial statement because not many systems satisfy these conditions. So let me just summarize what we have today. So we go through this important concept one more time. we discuss universal scaling function and universality class of different systems close to phase transitions. And we discuss the general question how this phase transition occurred, because something, the free energy, should be non-analytic, but where does this non-analyticity come from? At the finite size, we know that this is not possible because everything is finite and we don't have any chance to have a singularity or a jump or whatever. And therefore, this leaves us the only possibility to have a non-analytic behavior of the free energy density, which is in the thermodynamic limit. And the word thermodynamic limit is something new to, I believe, all of you, because that is really advanced concept in the context of statistical mechanics. But it's not unheard of, because in reality, all these experimental materials that you could measure in the lab are considered to be a system large enough that the system size goes to infinity. But again, not all these experimentally measurable systems that satisfy these conditions. And it depends on the interaction strength, for example, the power law exponent, and also the dimensionality of the system. Okay, so I guess that's give you a more concrete and precise ideas about what we are dealing with. What we are dealing with is the free energy or free energy density of many particles where the system can have a phase transition. And how can that occur? Well, because the free energy density can be non-analytic at phase transition. But how can that be? So that's our purpose for the next lectures. All right, so let's start. Last time we talked about the thermodynamic limit, and we mentioned that in order to satisfy the thermodynamic limit, the bulk and the surface free energy density should have a finite value when the volume of the system goes to infinity in the thermodynamic limit, and this condition is not easily satisfied. In many cases, we find that this cannot be satisfied, namely, the thermodynamic limit is not always existing. Okay, so let's study an example of that. So in this example, we can see that in some cases, the thermodynamic limit exists. In other cases, it doesn't exist. Okay, so this example is the power law interactions in the sphere, radius capital R, and there are particles distributed uniformly inside the sphere with the density fixed as a constant. And the interactions between or among these particles inside the sphere follows this power law behavior, which is 1 over distance r to the power of sigma, where the r is the distance between any two particles. So such as the inverse square law of Coulomb interactions among charged particles or this gravitational force. So, but in any case, let's just compute this energy of a sphere with uniform distributed particles and the interactions as a power law form, and let's just compute this kind of energy of, say, power law interacting particles inside the sphere. Okay, so this is the form of this. It's like a Coulomb energy of charged particles inside the sphere, but now we consider just some kind of uniformly distributed particles inside the sphere, and they interact by this inverse power law. All right, so then with the uniform distributed particles, this is simplified as this integral, where little d here represents this dimensionality, and in this case, it's a general dimension. So in 3 dimensions, this is a sphere, but it can be different in general. So then this integral becomes this. So then you could furthermore just change variables. You could see that this is going to be capital R to the power of 2d minus sigma. And you could just converge and convert this integral inside the unit sphere, where this x vector and x prime vector both are the vectors within the unit sphere. Okay, so this is what you are doing here. So this is x and this is x prime, unit sphere. In any case, you could just rescale this integral in terms of calculations over a unit sphere. And we'll see later that this integral here can be a constant, c independent of the radius r. So if this is the case, so suppose that this integral is actually a constant independent of radius r, then this bulk energy density, EB, which is defined as the total energy divided by the volume of the sphere, which is given by this A times rho square C times radius power 2d minus sigma. So you can see that you cancel this, the power r to the power of d, both in the numerator and denominator, and you get this energy density of the bulk, which is proportional to capital R to the power of d minus sigma. So then, but later we will more accurately determine this integral, this dr prime integral, more carefully, but this is just some kind of a hand-waving argument. So the thermodynamic limit is well defined if and only if sigma is greater than d. All right, so we will see that in just a moment, which means that if sigma is equal to d or sigma is less than d, and we have problem. So for sigma equal to d, this is some kind of a critical case where this bulk energy density will show logarithmic divergence as function of a radius. What happened when sigma is less than d? So this is proportional to some r to the power of, say, epsilon, which is positive. So when r goes to infinity, this bulk energy density will go to infinity as well, and this rule out that the thermodynamic limit exists. So clearly there is a criterion telling us that under what circumstances do we have or do we not to have the thermodynamic limit. So in this simple case calculations, we can find that the thermodynamic limit exists if and only if sigma is greater than d. But this is not a rigorous calculation, so we will more rigorously determine this integral over there, because we could still have a problem of convergence of the integral when x is almost the same as x prime. So you can see that when x is very close to x prime, this denominator vanishes, so this integral may blow up to infinity. So there may be some problem. So we need to more carefully evaluate this integral. So to fix this problem, we can impose so-called hardcore condition, meaning this interaction is actually zero inside the hard core, and it follows this power law decay out of this hard core. So which says that this lattice constant A, so when R is actually greater than A, you get this power law decay of this interaction, but when R is actually less than A, so you get zero interaction. Okay, so this is telling you that each particle has a finite size, and this finite size is about the radius little a here. So the minimum interaction, say, length is about a. So this interaction starts from this distance r, which is larger than a. So this is just a hardcore condition. So if we use this hardcore condition, and we can evaluate this by defining combinations of this x and x prime, which are u and v. So if u vector is a difference between this x and x prime divided by 2, and v is the average of this x and x prime vectors, where x and x prime vectors are defined over here within the unit sphere. So in terms of a u and v, you could evaluate this bulk energy density once again, which is given by this form. So here Vd is the volume of a unit sphere in d dimensions. So then this is prefactor, but what about this integral over dx and dx prime? Well, dx and dx prime now becomes dv and du. Remember that this interaction u depends only on the relative distance between this r and r prime, namely it depends only on u but not on v. So you could integrate over dv easily, and then you could perform another integral very straightforwardly. So let me just write down this relation in this calculation. So a is little a is actually this lattice constant of these particles on the lattice, and this a divided by r is the lower bound of the u, and 1 is the upper bound of the u. And this small volume integral du to the power of d is actually given by u to the power of d minus 1 times du times the solid angle. So with that kind of parameterization, so you could very easily evaluate this thing. So this is given by 1/2 A times rho square r to the power of d minus sigma times the surface area and times the integral. Now this lower and upper limit of the integration over du ranges from a over r to 1, and integrand kernel is u to the power of d minus sigma minus 1. So let me just give you the final answer after integration, so you could do that pretty easily at home. So the bulk energy density is given by this expression here. So it has two possible values. One is when sigma is different from d, which is this minus a over r, d minus sigma. So this is when d is not equal to sigma. And the second solution or value is this. This is when d equal to sigma. As I mentioned over there, that when d equals sigma, we get the logarithmic divergence of this bulk energy density. So again, you don't have a thermodynamic limit because now the bulk free energy density should be independent of this r, but here, in the case of d equals to sigma, you get the logarithmic dependence and divergence of this energy density as function of capital R. So now in this case, you don't have a thermodynamic limit. And for d is not equal to sigma, there are two cases. In one case, is that d is greater than sigma, and another case is d is less than sigma. So you could very clearly see that only when d is less than sigma do you get a finite constant bulk energy density which is independent of the radius capital R. So let's summarize our results of this bulk energy density in this power law decay interactions of a uniformly distributed particles in a d-dimensional system or d-dimensional sphere. And we obtain this expression more accurately. And so the bulk energy density is given by this expression for d is not equal to sigma. So I'm just interested in whether this quantity is a finite value which is independent of r, or it could blow up to infinity, or it could become 0. So this is all I want to know, the r dependence, the radius dependence of this energy density. So now I don't care about all these prefactors. I simply just collect all this capital R dependence of this function, and this is it inside the bracket. So there are two terms. One is a single term, which is dependent on this capital R to the power of d minus 6 sigma, and this is the most important term, turn out to be. The second term, you can see that it's a constant term because this R to the power of d minus sigma is going to be cancelled by the precisely the same factor in the denominator, so that the second term become a fixed constant value. So now let's look at the first term. So apparently when d is larger than sigma and this term blows up to become infinity, as a result you don't have such a thermodynamic limit. So no thermodynamic limit. However, when d is less than sigma, you get 0 because the power exponent here is actually negative, meaning when capital R goes to infinity, the first term vanishes, and therefore you have only the second term, which is a fixed constant, independent of radius. And this is what we are talking about. We do have a thermodynamic limit if and only if the dimensionality is actually smaller than the interaction, the power law exponent of the interaction strength. So in other words, in order to have the thermodynamic limit, we need to restrict the interaction to be a short-range interaction. Namely, the sigma is actually greater than your dimensionality. So if we study the three-dimensional system, and in order to have a thermodynamic limit such kind, we need to have a power law decay of the interaction with the exponent sigma, which is greater than 3, which is very short-ranged. So let me just plug it here. So this is u, and this is r, and we need to very short-ranged interaction, sigma, which is greater than d. All right? So this simple but interesting example tells us that in some cases the thermodynamic limit exists, but in other cases it doesn't exist. So let's discuss another very important terms, which is phase boundaries and phase transitions. So over time we could draw some phase diagrams in terms of coupling constant and so on. And we could have some phase boundaries between phase A and phase B, and a critical point or a tri-critical point or a critical endpoint, something like that. So we could define those phase boundaries and critical point in a more mathematical way. So assume that this FB exists in the thermodynamic limits when L goes to infinity. So we can have a precise definition of a phase boundary in the parameter space. Say, for example, if we have m coupling constant, which I call this K with a bracket, which represents a set of a collection of this coupling constant ranging from K1 up to Kd, where d is called the dimension of the coupling constants. There are d coupling constants. So in other words, this phase diagram is plotted in terms of this d-dimensional parameter space when you have a d coupling constants. So the phase diagram is in the parameter space of this collection of a coupling constant, which is in d dimensions. So for example, if we have just two coupling constants, K1 and K2, and we could have some phase boundaries like this, which indicates some different phases, A and B and C. For example, this liquid gas transition or solids, liquid and gas for some molecular systems, for example. And we know that whenever there's a phase transitions, the bulk free energy becomes singular or non-analytic at that point. This FB, as function of this coupling constant, is analytic everywhere except at the phase transitions. But this phase transition could be a critical point or a critical line or a critical phase. But the geometry, a shape of this critical point, critical line, and critical phase all live in this d-dimensional space, in this coupling constant space. And we could define dimensions of this non-analytic parts of this free energy density and following way. So the region where the free energy density is non-analytic has a dimension, which I call this ds. So this ds refers to this dimensions of the regions where the free energy density becomes non-analytic. And that region is a point, which means that the ds is actually zero-dimensional. If this is a critical line and this ds has one spatial dimensions, and if this is a phase, it could be two dimensions, and so on. Okay, and then we could define another very useful dimension called the codimensions, C, which is defined as this total dimensionality of your phase diagram, capital D, minus this ds, the dimensionality where this bulk free energy density shows non-analyticity. And this is actually invariant quantity, because if I simply just change this dimensionality of the coupling constant space, capital D, by +1, and correspondingly this ds, this dimensions where this FB becomes non-analytic, also shifts it by +1. However, my codimension is still the same. Okay, so this codimension is a very useful concept to actually define this phase boundary. So let's just define this phase boundary. So when c equals to 1, we refers to a phase boundary. But when c is greater than 1, it refers to some critical points or surface. So let's just go back to this example here in terms of a two coupling constant phase diagram. Say, for example, this K2 is actually what? Some pressure, and K1 is what? Is some temperature. So let me just redraw this phase diagram of a liquid gas transition. So we have such a phase diagram. This is a solid phase, and this is a gas, and this is fluid. And so you could check that along this phase boundary, you have a codimension c equals to 1, and So it's here, but right here, this is called tri-critical point or triple point. You have C equals to 2. And interestingly, there's another, it's called a critical point right here. This is some kind of a critical endpoint, which we call this critical endpoint or critical point, which shows codimensions being 2. And as we mentioned last time, that we could go from one phase to another either by passing through this phase boundary, or you could get around with the phase boundary by a detour. So suppose you change your pressure or temperature in such a way that you can pass this solid liquid phase boundary. It's called the phase boundary. Or you could cross this liquid gas transition like here, or you could even cross the solid gas transition over there. But interestingly, you could avoid passing through the phase boundary between the liquid gas phase, and that's what we have discussed last time, that we could change the temperature and pressure in such a way that you start from this gas phase and then you make a detour and then you end up in the fluid or liquid phase without passing through this phase boundary. So we can ask, why is that? Why can we have a detour without passing through this phase boundary? And we will see later the reason. Okay? So the reason is that both the liquid and gas in this case share the same symmetry. So because the liquid and gas have the same symmetry, so oftentimes when we have a phase transition, we break some symmetry or we preserve some symmetry. For example, if we go from this spin-ordered phase where all the spins are aligned in a particular direction, then we break the spin rotational symmetry. So suppose we have phase transitions like this, and on the one side you have all spins aligned along the particular direction, so that the spin rotational symmetry is broken by choosing a particular direction for the spins to align, and so this is the so-called the symmetry breaking state. So we will talk about that. This breaks the symmetry. However, if we increase the temperature so that the spins are randomly oriented, then we are in this paramagnetic phase or spin disordered phase. In that case, spins can point to any direction in three-dimensional space. So there's no symmetry breaking in the system, so that when the spins point to any directions, it's allowed. And so this Hamiltonian system preserves the spin rotational symmetry. So we have this spin rotational symmetry. In other words, in this simple case like icing spin, in the presence of the temperature or thermal fluctuations, so you have two phases. One breaks the spin rotational symmetry, another preserves the spin rotational symmetry. So the phase transition is actually a signature of such symmetry changes. So if the liquid gas have the same symmetry, so then there is no distinction between the liquid and gas. So in principle, we can have a detour so that you don't see any phase transition. But of course, if we particularly choose a particular path of this parameter space, then we do see a phase transition. So whether or not we see or we don't see the phase transition, in this liquid gas transition, we have two possible tours or two possible ways to either see or not see the liquid gas transition. So that is because they share the same symmetry. So I think time is up, and next time we will define more formally two types of the phase transition, the first order and the second order or continuous phase transition, and we will define the correlation length where it diverges at the transition. So I encourage you to read our textbook and my lecture notes, which will be sent to you by E3. All right, okay, so I'll see you next time.